Okay. So this morning we tackle stability, right? Stability, clouds, and precipitation. I don't think we'll get to clouds and precipitation. We'll see how we go. The first part is going to be a fairly methodical and I think pretty slow walk through the components of stability. I think I mentioned this on Tuesday. This material will be the first part that I think will tee you up for the understanding of the take-home exercise, right? That thermodiagram that we're going to talk more specifically about in an entirely separate lecture. But this is the kind of framing and the precursor for all that. Pretty important. So let's see how we do. The starting point here, let me go back. I know it's made another appearance, is the saturation vapor pressure curve here. Well, whoever teaches in here, they're stealing things. So in talking through the saturation vapor pressure curve, right, the role of water in the atmosphere, we just cast our mind back to this discussion we were talking about putting a parcel of air on this diagram. And we're going to talk a lot this morning about parcels of air. See if you can just familiarize yourself or be comfortable with that idea. A meteorologist, when they're talking about the atmosphere and what kind of state the atmosphere is in, they literally go out and think about a bubble or parcel of air and how that would behave relative to the surrounding environment. It sounds a little bizarre, right? But if you're really trying to understand the dynamics of the atmosphere, that's the way in which we do it. So we've spent a lot of time talking about putting a parcel on here, and it has a certain vapor pressure, and you can either shovel more moisture in, right, and get it to a saturated vapor pressure. The vapor pressure divided by the saturated vapor pressure gives you the relative humidity. We've done all that. We've talked about cooling a parcel of air, much easier to its viewpoint, okay, where its relative humidity is 100%. And that whole concept is key to, one, getting a parcel of air onto this curve so that it becomes saturated. And then what happens if you continue to cool it, right? It slides down that curve. Let's say it stops here. It's still saturated. But the difference in the vapor pressure between these 2 points, all of this shaded area, is what we then see manifest as cloud. Condensation begins to occur, right? Relative humidity stays 100% and you start getting clouds and so on. So all of that is the kind of precursor to stability, to understanding stability, because a lot of this has all been couched in terms of getting a parcel onto that curve, cooling a parcel of air to get it onto that curve, right? And we've already talked about what's the easiest way to cool a parcel of air. It's to do what? To lift, right? So if you can take your bubble and lift it, it will cool by expansion as it moves into slightly decreasing pressures, okay? And as those air molecules have longer distances to move, relatively speaking, within that parcel, that manifests itself up as a lower temperature, right? Because temperature is just the average speed of the molecular movement. So all of that is a whole lot of ifs if we can get the parcel onto the curve, if we can keep lifting them. So today we talk about stability, and this whole discussion of stability comes to us from the premise of, is the atmosphere conducive to lifting or not? That's the bottom line. That's what this whole lecture is about, okay? Is the atmosphere in a position where it wants to support uplift? Because if it's supporting uplift, then it is supporting the air parcel sliding towards the saturation vapor pressure curve, right? And if it's not, if the atmosphere is not in that position and it wants to suppress upward movement, then it's going to cause that parcel of air to slide back towards the right, right? You're not going to get onto the saturated vapor pressure curve, and you have no chance of forming cloud or forming rain. Okay, so does that concept make sense to everybody? We're looking at the state of the atmosphere, kind of like the State of the Union address. Let's go out and see what the state of the atmosphere is at any given moment in time, at any particular place. And is that atmosphere supportive of uplift or not? Okay, so that's what stability is. And then if it is, obviously we can then start to talk about clouds, and we'll spend a relatively short amount of time looking at clouds and the classification of clouds. And then ultimately, if you want rainfall, then we've got to keep going, because then we've got to do some other things to actually generate rainfall or snow or sleet or freezing rain or whatever the type of precipitation is, right? But it all comes down to the state of the atmosphere, right? Now, just as a heads up, before we get going, the atmosphere might be in a state where it has no interest in supporting uplift. It may just want to keep everything where it is. That doesn't mean to say you can't get clouds or a severe storm, because what can you do? You can bring a front in and force that air to rise, right? The atmosphere may have no interest in that, but if you force a front in, that air is going to rise. Or if that air, comes into contact with some kind of barrier, a mountain, then it'll rise. So we're talking here about, in a free atmosphere, is it conducive to uplift or not? That's the question we need to answer this morning. And it all comes down to this term, stability. All right. All good. Okay. So how does this work? How do we determine the stability of the system? So every day, I think it's 7 a.m. Eastern time and 7 p.m. Eastern time, the National Weather Service releases about 92-ish, depending on who's awake at what particular time. About somewhere between 90 to 95 weather balloons are released in the US. Each of these dots is an official recording station around the world. But in the US, the National Weather Service releases just more than 90 of these. These weather balloons have a radio sonde at the bottom attached to it, okay, with a little note saying this is a weather instrument. If you please find this, return it to the following address. And they send them up every 12 hours. And as that radio sonde goes up, it sends back data on wind direction, wind speed, atmospheric moisture, pressure, and so on. It sends back all the variables that you would want to put into a station model, okay? And you can see some regions, right, like places in Europe and the United States are pretty densely covered. Others are not. Okay? Australia is a big place. And the official weather balloons are fairly well dispersed, right? So right off the bat, we don't have measurements of these variables for every square kilometer, obviously, right? You'd be sending up hundreds of millions of balloons, and that's just not feasible, both environmentally and certainly from a financial standpoint. We'll talk a little bit about that when we look at weather forecasting, right? So if I'm sitting here in DFW and say Logan's up in Oklahoma City and there's nothing between us, and he releases a weather balloon and I release a weather balloon, that's two sets of data, but pretty far apart. We have to start interpolating and making assumptions of what's going on between those 2 points. I make that point here, everyone, because that, as we'll see later, will introduce the dreaded term error into weather forecasting, right? So if you want to make a forecast, you're going to have to look at both of us and start interpolating the data, what the atmosphere might be doing above you. That's just the way it is, right? Fortunately, computers do that pretty well, but never perfectly. So the data we get on what's happening in terms of the state of the atmosphere comes from these radio sondes, again, every 12 hours, right? So each day we get somewhere between 180 to 200 sets of data coming back. If the atmosphere is very tricky, or if it, in particular, if there's the potential for severe weather outbreaks, they'll send up more and they'll do them more frequently. They might send them up every 3 to 6 hours. But generally speaking, we get this data 2 times a day. That data comes back to the National Weather Service. It's all processed and it produces what is known as a sounding. Okay, and a sounding is a vertical profile of what's going on in the atmosphere. And I'll show you what a sounding is. Yeah.
Is there a reason why balloons are like better than like other methods like radar?
Yeah, it's a great question. And so the answer is yes. Nothing beats the actual instrumented data. Okay, and they're full with a certain pressure and they go up at a pretty reasonable speed. I don't know what the actual vertical ascent is on these things, but nothing beats the real data. So we certainly augmented with radar and things like that. But in terms of looking at the actual pressure profiles, gotta have the real data. Good question.
If you come back down to earth, there's.
They explode, yeah, they pop. So they get up to about 100,000 feet, and then they pop. And that's just,
Someone get them.
yeah, and they come back, and here's this little red parachute that comes on back, and I've never seen one myself, but about 180 of these coming back down every day. Cool. Okay, so that's how we get the data, okay, to produce these vertical sound. All right, now I'm going to introduce you to something bizarre, but super important. Before I erase that, I don't know if you've gotten the impression or how you've thought about this in all of the way in which I couched this on we want to get air to go up, right? We want to get air to cool, to slide towards its saturation vapor pressure curve. I don't know in your mind if you're just leaving it at that, and that's great, or whether you're thinking about how fast that uplift actually is, okay? So this next slide here and the way in which I've annotated this is going to seem a little odd, but it is important to illustrate one point, and that is that when we look at the atmosphere as a whole and we're talking about uplift, don't get the impression that the atmosphere is going violently up or violently down, right? When we talk about the trigger to get air to start going up, it's very, very gentle, okay? Generally speaking. So here's what this looks like. Here's what I mean. And I've taken this from the book. Let's just look at the right-hand side for a second. Here's a satellite image. Is it visible or infrared? Exam number oneers. Just looking at the top right. Visible or infrared? Visible. Anybody want to advocate for infrared? Okay, good. Yeah. Why would you say infrared? What's the giveaway?
This is gray and white clouds.
Yeah, there's gray and white on the same image. Now you will get more experience, and especially when you start looking at this system here, which is a mid-latitude storm. I know we haven't done that yet, but we will. Okay, and you start looking at these areas here with gray. So that's an infrared image of a large storm system almost 15 years ago now, October the 27th, a large mid-latitude cycle. Okay, on the left, and this is where things are going to get a little bizarre, but hang in there. On the left is a map of vertical velocity, right? So actual vertical speeds across the United States at the 700 millibar level. So about how many kilometers up do you think we are, just as a guess? 700 millibar level? Someone give me a...
3,000.
Yeah, 3 kilometers, 3,000 meters, good. That's 1-2 part. 500 millibars is 5 kilometers. 700 millibars is 3 kilometers. Why do we look at 700 millibars? Because that's where the action occurs, right? 850 is about 1.5 kilometers. That's generally where the base of the clouds are, very, very generally. And about 3 kilometers up, you're definitely within the kind of inner workings of most storm systems. And this map here shows the 700 millibar vertical velocity in millibars per second. Now, you may think, wait a minute, why aren't they doing this in feet per second, in miles per hour, or whatever? So computationally, meteorologists use millibars per second, okay? And I'll show you just how we convert that. And the funky thing about this is that the negative values show vertical uplift, right? The positive values show sinking. Okay, that may seem a little backward. And the reason why the negative values show uplift is that what always decreases with height? Pressure decreases with height, right? So as the pressure decreases with height, a negative value shows vertical motions. If you can't wrap your head around that, that's perfectly okay. Then just park. A minus sign means air is going up, okay? So the purples here, our nice little purple color, the more negative value, the faster the air is going up, right? And the redder the color, the air is sinking. So we've got 3 big purple blobs at 700 millibars. We've got one off the Pacific Northwest, and that's around the corner, you can't see it. And then there's a lot of vertical uplift here and a lot of vertical uplift in the center of the low. Right? That's air going up quickly. Does that make sense? So what do we mean by quickly? So here's where things get interesting, right? Let's see if this works. So let's take the central pressure here for a moment, right? When I looked at, I went into the archive, this was just an image from the book, and then I went into the archive to look at what the central pressure was along that frontal boundary. It was 955.2 millibars. Okay. On a station model, you would see 55.2. You'd have to decide if it's 9 or 10. You could have put a 10 in there because 1055, but you're in the middle of a storm system, right? So it's 955.2 millibars. Are you with me? That's a deep low in the middle of the storm system. Okay. And the purple bullseyes here are minus 0.004 millibars per second of vertical motion. Okay. So here's how things get quite interesting. So the vertical velocities, let's take the fastest speeds, are 0.004, minus 0.004 millibars per second. Are you with me? And that's still like, okay, well, what does that mean? So here's what it means. If you go from 850 millibars, let's assume that the lifting condensation level was 850 millibars, 1.5 kilometers off the ground. Is everybody with me there? Can you picture what I'm getting at here? So you're at the surface, you're at 1.5 kilometers, now we're at the lifting condensation level, and then the map here is going to 3 kilometers up, 3,000 meters, right? So from 850 millibars, in other words, the assumed lifting condensation level, to 700 millibars, that's 150 millibars of change in pressure, right? 150 millibars. And over that 150 millibars, the pressure tendency or the vertical velocities are 0.004 millibars per second. Right? Everybody with me? So we come into the storm and we say, all right, someone's at 1.5 kilometers, someone's at 3 kilometers. Okay, we're looking at 850 to 750 millibars. Over that 1.5 kilometers, the vertical velocities here were 0.004 millibars per second. So if you just take the pressure difference divided by that vertical velocity, how many millibars divided by how many millibars per second, it turns out that 150 divided by 0.004 comes out to 37,500 seconds. Okay, what is 37,500 seconds? About 10.5 hours. What that means, okay, is that between 1.5 kilometers, the base of the cloud, to 3 kilometers, that air is rising, and it would take about 10.5 hours for it to rise just that 1.5 kilometers. Does that make sense? Doesn't sound like very much. 10.5 hours, half a day, for the air to go 1.5 kilometers. Okay. It's a really important point because when you look at large storms like this and we start thinking about uplift, stability, what kind of trigger do you need to get air to go up? The air inside these large scale geographic areas isn't doing this. Okay, it's not doing that because even though the pressure gradients are steep, right, gravity pulls it all back down together.
So is that considered a short amount of time or a long amount?
That's considered a pretty short amount of time over
That distance?
yeah at that distance over these scales. Now, having said that, this is very different. Whoops, this is totally different when we're talking about an isolated thunderstorm. All right. How many of you have sat on a summer's afternoon and seen a thunderstorm develop in 10, 15, 20 minutes, 30 minutes, right? Where you start seeing the billowing clouds starting out at 1 kilometer or 2 kilometers, and within half an hour, that cloud is 35,000 feet, right? Or a plane flying through a thunderstorm, it's why the pilots avoid them. You go through a thunderstorm and you get this turbulence, right? This is not causing turbulence, okay? Gentle uplift over large regions in the space of 10 hours to lift 1.5 kilometers. But within storm systems, individual parcels of air, that vertical uplift can be much more rapid. That's the big point I just wanted to get across at the outset, and I think the book does a pretty good job of contextualizing that, right? Because remember when we first got together and I showed you a graph that had time and spatial scale on it, and I said we're going to be dealing with very small time intervals and spatial scales like little microturbulence and large spatial scales like hurricanes that last for several days. We're going to be sliding up and down that. Kind of what we're doing here, right? We're sliding up and down the scale, looking at, let's say the floor, I'll get you in a second, Ryan. Let's say the floor of this classroom represents the United States. Okay, if the air is rising relatively quickly, to Audrey's point, it would still be going up, very, very gently. Okay, the atmosphere might be conducive to gentle uplift, okay? And then suddenly over here, we've got a thunderstorm developing for all sorts of reasons that we're going to get to, and that uplift can be extremely rapid. Does that sort of make sense? Right.
So, is the uplift rapid in thunderstorms because the energy they?
Yeah, the uplift is rapid in thunderstorms because of things we're still going to get to this morning. You'll see. Yeah, we'll see. So again, I don't want to confuse. Take a step back and just think of, is the entire atmosphere in this room conducive to uplift? If it is, at vertical velocities of 0.004 millibars per second, where in 1.5 kilometers, I should have actually done the exact conversion, right? 10.5 hours to go 1.5 kilometers. I mean, super, super gentle. That would be enough to do lots of things, but it wouldn't be enough to cause a thunderstorm over Rachel's head. Other things have to happen.
So, is the 0.04 then? Is that 0.04 is like the fastest and slowest?
No, that's not the end.
It's
I mean,
just
I've seen maps at 0.008. So
and it's slow.
it's slow, right? So 0.008 would be uplift over the space of about 5 hours.
Just like theoretically speaking, like if the whole atmosphere was kind of like a thunderstorm, like what would happen? It would just have like really extreme weather all the time.
Yeah, but the atmosphere loves hydrostatic equilibrium.
Yeah.
So it wouldn't allow that. Okay, does that sort of make sense at the outlet, right? So again, we're talking about, is the atmosphere conducive to up? Okay, so let's get to stability. So please keep thinking here throughout the rest of the morning, throughout the rest of this class, right? In terms of parcels of air, bubbles of air. What would happen if I took a bubble of air, okay, and put it right over here over this parking lot here and heat it? How would that air rise and expand? How far would it go relative to all of the surrounding air? So we'll take a well-known example, right? Islands, physical geographic islands sitting out in the ocean, right? Because of the specific heat differences between land and water. So we've already said water heats up much more slowly than land, right? We know that. So what would happen if the atmosphere around this island, so it was, let's say it was pretty cool over the ocean and then temperature decreased with height. If the sun came up and heated that island, what happens to the air in contact with the ground? It warms up, right? And that warm air begins to rise because it is buoyant, relatively speaking to the surrounding air, buoyancy. So buoyancy is another course. We haven't talked specifically about buoyancy. Oh crap, am I going to spell it? Is it B-U-O? No, I'm not even going to try and spell it. Buoyancy. Okay, this is why we have AI to type in. So as you heat air, it rises because it has a net upward force. It becomes more buoyant than the surrounding air. It's like taking a little rubber ducky. Okay, you should all take a little rubber ducky into the bathtub and you let it float on the surface. And if you plunge it to the bottom of the bathtub and let it go, what happens? It comes straight up to the surface, right? Because it is more buoyant than the surrounding water, right? That upward force, that buoyancy, is related to the weight of the water that is being displaced by the rubber ducky. Right? If you had a big rubber ducky and you took it down, you would displace more water. There would be a greater upward buoyancy. So the air above this island becomes buoyant. That's why warm air rises. Okay, you heat the warm air, you heat the ground heats the air in contact with the ground it decreases the density, it increases the buoyancy, and it begins to rise. And so that warm air begins to rise, and as it rises above that island, slowly starts rising above that island, it begins to cool, right? By expansion. It has to, because pressure is decreasing with height. And as it rises a bit further, it gets cooler and cooler and cooler. And the rest of the morning, this whole thing about stability, this entire concept, looks at what is the temperature of the parcel of air relative to the surrounding environment. That's the key for the rest of this morning. We're going to be looking at, will this air continue to rise or not? And how do you determine it? You look at the temperature of the parcel relative to what the ambient environment is. Okay?
Does the warm air rise because it's less dense?
Yes. Yeah. Okay. Okay. All good. All right. Good-ish. Okay. You're going to see lots of diagrams like this. So for the rest of the morning, we're going to spend a little bit of time talking about changes in temperature with height. So Z or Z, as you like to call it, is elevation, and T is temperature. We're not going to have any numbers on these diagrams, right? We're just going to keep it super simple and clean. Again, just as a reminder, right? Height is not a function of temperature. I know in math, you always look at the independent variable and the dependent variable, right? The dependent variable is y depends on x. But in meteorology, we just flip them because it's easier to interpret. It makes sense to look at how temperature changes with height variable. So this is height and this is temperature. Okay. So we send up a weather balloon and it sends back a temperature reading. Okay? A temperature reading. And that change in temperature with height is known as a lapse rate. A lapse rate, the change in temperature with height. Okay? The actual change in temperature with height. So after that balloon goes up and it sends back the data, you get a blue line like this, and that is your actual lapse rate. We refer to that also as the ELR, the environmental lapse rate. What is the actual environmental rate of change with height? So that's one acronym I want you to get down. There'll be a couple more this morning as we go through. ELR, environmental lapse rate. Okay, actual change in temperature with height. Okay, cool. Now, here's a very dull and boring slide, but it captures this all. So let me explain this, and then we'll go back to looking at this vertically. Okay. So we have an environmental lapse rate, the ELR, and it's the temperature of the ambient air. What is the actual change in the temperature of the environment? And on average, this is clearly on average, it's about 6.5 degrees Celsius per kilometer. We're going to have to work in Celsius and kilometers here, because working in Fahrenheit and yards and feet and fathoms just doesn't work. Right? Because it's much easier. The world all uses, even the US, uses degrees Celsius and kilometers for these calculations. So we've got the actual change in temperature with height. And again, on average, that's 6.5 degrees Celsius per kilometer, but that will change minute, by hour, by day, depending on what the atmosphere is doing. Okay. Then we have the next acronym, the DALR. This is the dry adiabatic lapse rate. Okay. This will impress your family if you can explain the DALR over spring break. The dry adiabatic lapse rate. Okay. So what's the dry adiabatic lapse rate? That's the rate at which a parcel will cool if you lift it in the atmosphere, if it is not saturated, right? So the dry adiabatic lapse rate refers to any parcel sitting down here in relation to the vapor pressure temperature curve. Unsaturated air. If it's dry, which by definition means it's unsaturated, and you lift it, it's going to cool, and it's going to cool at a set rate, 1 degree Celsius per 100 meters, 10 degrees Celsius per kilometer. Okay? Nice and rapid. So that little bubble of air sitting above that island, okay, if that bubble of air is this parcel here and it's unsaturated and you lift it and cool it, and it starts cooling, it's going to cool at the DALR, the dry adiabatic lapse rate, non-negotiable, 1 degree per 100 meters.
Why is it that rate? Why is it?
Because it just is.
Okay.
That's just how the physics works. One of those, it is what it is. But I'm going to ask you another question in just a second. Okay. However, and here's the but, parcel gets onto the saturated vapor pressure curve. It's now saturated. its relative humidity is 100%. If your air is saturated and you somehow continue to lift it, then it's going to cool at a different rate. And it's going to cool at not a set rate. And that is called the saturated adiabatic lapse rate. Oh, incidentally, the term adiabatic is, I mean, it's real, but it's a bit difficult to deal. Adiabatic just in the atmosphere means there's no actual heat exchange between the environment and the parcel. So if Audrey's got a bubble of air sitting above her head and it starts rising, okay, it will cool if it's unsaturated at the dry adiabatic lapse rate, assuming there's no heat exchange between the ambient environment and her bubble. Is that really true? Probably not, but we can't deal with that. But as soon as it becomes saturated, then the rate of cooling changes, and it changes at the SALR.
So then how is the drying, like, how is that a set term or like a set number if there's always gonna be flow between
Because it's
two?
pretty, I mean, it is a set number. So when if you have no heat exchange, if you have no heat exchange, and you do this experimentally in the lab, it does cool at 1 degree per kilometer. And in broad areas, if we're talking about, you know, bubble, an air parcel sitting above the metroplex, okay, and you start getting that air to rise, okay, there won't be any internal heat exchange between that conceptual bubble and, you know what I mean? It's tough. On the boundaries of the parcel, there will be heat exchange. So saturated adiabatic lapse rate, right? What's the saturated adiabatic lapse rate? The saturated adiabatic lapse rate varies, okay, between about 0.6 degrees Celsius per 100 meters to about 0.999-ish degrees Celsius per 100 meters, okay? Or about 6 degrees Celsius per kilometer, right? So the dry rate is 10 degrees Celsius per kilometer or 1 degree Celsius per 100 meters. The saturated rate is about 6 degrees Celsius per kilometer on average, but it varies. So now I'm going to come straight back to Ryan to ask the question. If the dry rate is set, why do you think the saturated rate varies? Ooh, someone's got to answer this. This is another one of the take your A and run.
There's some different temperatures,
Hmm?
different temperatures, like different amounts of energy,
Showing a bit?
like less or more energy. Person.
Mm-hmm.
More or less water vapor, and the water vapor has the high specific heat. So that changes how much heat is absorbed.
Exactly. And how much heat is potentially released? Because what kind of heat do we talk about when water is evaporating? Latent heat. It's latent heat, right? So when your air parcel, it's dry, relative humidity of 50%, 70%, 98, 99, relative humidity of 100%. Air is saturated. Now, if it's going to continue to cool, it slides down here. Relative humidity is still 100%, right? But what is it releasing as it's sliding down there? It's forming cloud, meaning water is changing phase, right? From water vapor back into liquid water. And as it changes phase into liquid water, it releases the latent heat, which warms the parcel and suppresses the cooling rate. It says, chill, just relax. You're not going to cool at 1 degree Celsius per kilometer per 100 meters. You're going to cool at a lower rate because I am releasing now real sensible heat, suppressing your cooling rate, right? And so to your point, the more moisture in the atmosphere, right, the greater that suppression is. So if you're in a super humid environment, if you're marching around New Orleans and you've got clouds above you, right, your cooling rate is going to be much more like this. Okay, it's going to be a much slower rate of cooling in a saturated parcel of air than it is in a almost dry parcel of air. Does that make sense? So 3 big rates: the environmental lapse rate, it's the ambient temperature, the dry rate, if your parcel is unsaturated, and the saturated rate if it is.
So as the parcel of air goes down the saturation vapor curve, do more and more clouds form?
Has to. Exactly. Starting to put the pieces together here. Beautiful. All good. I get a sense it is. That's a good thing. All right. So let's then talk about stability. Okay, that's all teeing it up for stability. So what we're going to do here, again, remember, all we're doing, okay, once you've got those three rates down, okay, an environmental rate that is what it is, whatever your radiosonde sends back, your dry rate that is 1 degree Celsius per 100 meters, and your saturated rate, which is variable, depending on the moisture content. Now we're going to compare the temperature in your parcel to the ambient air, right? So let's say you've got your parcel of air sitting here at the surface. So we go out onto the Sidbridge patio. There's our bubble of air. Everybody's holding onto this parcel of air, okay? And let's say the blue line here is the actual lapse rate, right? So Sloan sends up the weather balloon and it comes back, and this is what she plots. She plots the environmental lapse rate, the ELR, the actual lapse rate temperature with height. That's what it looks like, okay? And let's say your parcel is right here, and I should have drawn these right on top of one another, but they're right next to one another. And let's say you take your parcel here and it's unsaturated and starts rising and expanding, okay? Now, let's not assume it's going to rise. Let's say that we have a gigantic tall, I know this sounds dumb, but let's say we've got a huge gigantic step ladder that goes up several hundred kilometers, right? And you take that parcel, and I say to you, okay, grab that parcel, now start climbing that ladder. And you take the parcel up, and you start dragging that parcel up. And as you're dragging it up, what's the parcel doing? It's expanding, and it's cooling at 1 degree Celsius per 100 meters, right? And we get to this elevation here, okay? And I say, just take your hands off the parcel. Will the parcel stay there? Will it continue to rise, or will it go back down to its original location? That's the crux of stability. When you take your hands off the parcel, what is it going to do? It's going to stay there, rise, or sink. And all you've got to do is compare the temperature in your parcel to the temperature of the surrounding air. If the temperature in your parcel is the same as the surrounding air, it's going to stay right there. And that's what we call a neutral atmosphere, which is relatively rare. Okay? However, if your parcel temperature is either higher or lower than the surrounding atmosphere, something else is going to happen, right? So that's a fairly rare situation. Let's say this is the situation. Let's say we're out on the Sidbridge patio. We come back an hour later and Sloan says, hang on a second, guys, we've got a different lapse rate here. My weather balloon has plotted this lapse rate here in blue. That's the environmental lapse rate, right? And now it's Nick's turn, and he gets onto the ladder and he starts dragging the parcel up, and it starts cooling by expansion. Remember, all of this is still couched under the assumption that it's unsaturated, okay? So it's plotted somewhere down in the unsaturated zone on the SVP curve. And we go up here and we get to say 2 kilometers, and I say, okay, Nick, take your hands off the parcel, all right? What happens? The temperature of that parcel at this elevation, so from now on all of these graphs, just go to the elevation and look at the temperature in your parcel relative to the temperature of the ambient environment at that elevation. And what happens? The temperature in your parcel is less than the temperature of the ambient environment. Does that make sense? If the temperature in your parcel is less than the ambient air, what does the parcel do? It begins to sink back down, because it's colder than the surrounding environment, denser. That's a stable atmosphere. In other words, that atmosphere is not conducive to upward. Take your hand off the parcel and the parcel just begins to sink back down towards the surface. Okay? Does everybody see that? I know when I learned this, 1985, my first meteorology class, and we all for the exam, we just memorized it. If your dry adiabatic lapse rate lies to the left, then it's stable. That's fine, but I want you to understand just the basic physics behind it, right? This is a stable atmosphere, not because the DAR lies to the left of the environmental lapse rate. It is because at each elevation you go up, at every elevation you go, temperature in that parcel remains cooler than the ambient air, so it'll sink back down. That's a stable environment. Okay. another way to think of this, and it's a good way to start thinking of this, is that the more vertical your environmental lapse rate, in other words, the more gentle the gradient, right? The slower the change in temperature of height, the more stable the atmosphere is.
How did, I mean, I understand the hypothetical, like us lifting the parcel thereof, but would that even happen?
Yes, we're gonna get to that. Yes,
How would
yes.
that even happen?
You'll see. No, it's a great question, right? We don't have Nick on the ladder, clearly, right? So you've gotta have, what's the word? What's the trigger that's gonna do this? What is gonna trigger this parcel to rise or not rise? We're gonna get there in a second. Good question, important question, right? Because all these hypotheticals are great, but you know, we've got to get something in the
I'm just
atmosphere.
curious if there's temperatures, if the actual lapse rate is already warmer than the dry inlet, and why would the dry inlet rise? Like,
We're gonna get there. In this case, it wouldn't. It wouldn't, right? You go out onto
Okay,
the,
okay.
we go out onto the patio and say, what's going on? Nick, look up in the sky, and he goes, well, it's a beautiful clear sky and there's not a cloud in the sky, we've got no rain. Well, yeah, because the atmosphere is stable. A stable atmosphere suppresses up. Okay? Unless you have a trigger, which we are going to get to. It's a really good question. So here's the other end of the other side of the coin, right? An unstable atmosphere would look like this, where your lapse rate is steep. In other words, your change in the environmental temperature is rapid, right? It's fallen over to the left. So as you go up with elevation here, your temperature changes much more rapidly. Okay. And skeptical Aubrey, who still doesn't, if she's going to take this, and now we're going to drag it up here. And in that situation, at any elevation, the temperature inside your parcel is warmer than the environment. So you take your hands off it, and it'll continue to rise. That's unstable environment. So we've got a neutral. We'll probably never talk about neutral again because it's so fleeting. And we've got stability and instability. Stable versus unstable, right? Which one do you want if you want a thunderstorm? Well, clearly you want an unstable atmosphere. You want an atmosphere that is conducive to uplift. Doesn't mean to say it'll happen. You may not have the trigger, but it is just conducive to uplift. Everybody there? All good, all good? Okay, cool. So here's the summary. We haven't even dealt with the moist adiabatic lapse rate yet. Here's the summary of a steep actual lapse rate and a gentle actual lapse rate relative to a dry adiabatic lapse rate. Okay, you just look at any elevation, the temperature in the parcel here, okay, and the temperature of the environment relative to the temperature of the parcel. That's unstable. Temperature of the environment relative to the temperature of the parcel. Temperature of the parcel is cooler than the environment, that must be stable.
Why aren't the actual lapse rates, linear?
Why are they these? These are just simply, this is just simply a reflection of exactly what the environment is at any given moment in time. I'm actually going to go on and show you the live one above Fort Worth now, so you can see what that looks like. Okay. Don't think linear or unlinear, just think, because you can come back and you can have a lapse rate that does that. Right. Temperature is increasing with time. We'll talk about that as well. Everybody good there? Okay, so all you're doing is comparing temperatures in parcels to temperatures of the ambient air. Well, yuck. Now we've got to bring in the moist or the saturated adiabatic lapse rate. The saturated adiabatic lapse rate is a lapse rate that changes. It's not 1 degree per 100 meters. It's variable because of the amount of moisture in the atmosphere, and as that moisture is condensing into real cloud, it's releasing latent heat. So this is a simple summary of the dry adiabatic lapse rate is linear, period, 1 degree per 100 meters. The saturated adiabatic lapse rate changes. It's a curve, right? Depending on how much moisture there is. On average, about 6 degrees per kilometer, 0.6 degrees Celsius per 100 meters in pretty moist air. Okay, but it can get close to the dry rate, but it's not constant. All right, awesome. Okay. Oh crap, there's another type of instability. Okay, and this is the one that is much more common than either purely stable or purely unstable. And it's conditional instability. And it's kind of the lead on would be from your question, why, what? Will that bubble go up or not? What, and conditional instability is, so the simple way to remember it, and then I want you to just try and understand really what's going on. The simple way to remember conditional instability is where the actual environmental lapse rate lies between the dry and the moist. So that's the simple, if I gave you a graph and said, what kind of instability is this? You can just remember that. Okay, cool. The environmental lapse rate lies between the dry and the saturated. Okay. That's conditional instability. The physical reality is that you can go to any elevation in the atmosphere. So if you went up to 3 kilometers above Fort Worth right now, okay, and you started at that point at 3 kilometers, and you wanted to determine if your parcel there at 3 kilometers is stable or unstable, right? It's really going to depend on whether it's saturated or not. That's the bottom line. So here's your initial position. Actually, it's 2 kilometers. Here's your initial position right now at 2 kilometers. And I ask you, what is the stability of the atmosphere here? Is it stable or unstable? And you can nicely say, well, it depends. If it's unsaturated, in other words, if the air is really dry and it hasn't reached its saturated rate yet, it will then rise and cool at the dry adiabatic lapse rate, right? Along this 1 degree. You just start from your initial position and draw your dry adiabatic lapse rate. Does that make sense? So how would you describe the atmosphere here based on an unsaturated parcel of air? Is it stable or unstable?
Unstable.
Why? Yeah, that's the way I remembered it. It's to the left. The dry adiabat is to the left of the environment. Physically, it's because the temperature here is less than the temperature there. So in other words, this parcel of air is going to sink back down. So they haven't got our trigger, right? But if you just try to give it a bump there and say we're going to go from 2 to 2.1 kilometers, yeah, it's going to come back down if it's dry. However, if it's reached its saturation vapor pressure curve and it's saturated, then what happens? It will rise at the saturated adiabatic lapse rate, at the curved moist adiabatic lapse rate. Now is it stable or unstable? Now it's unstable, right? Because it lies to the right, or the temperature in your parcel here is always higher than that ambient atmosphere. So stability in the atmosphere really is conditional, depending on where you are and whether you're saturated or not. That's the bottom line.
So neither are stable.
Say again?
Neither are stable.
No, this is stable. If it's unsaturated, it's stable. If it's saturated, it's unstable, right? The implication of that is huge, folks. The implication is that if you can bring a parcel of air to saturation, okay, if you can get it onto your saturation vapor pressure curve, it's much more likely to rise because it's probably going to be warmer than the ambient environment, because as it's rising, it's cooling at a suppressed rate, right? And the reality is, when you get to about 2 kilometers to 2.5 kilometers, you're probably beyond the lifting condensation level anyway, right? So moisture determines the rate of rise.
So can you have a like moist in that curve that's to the left of the surrounding? In this model?
Absolutely, you can.
Can you have it in this one now?
Well, what you would have to do, Brian, is let's go back to Sloan, because she's got the weather, she's the queen of weather balloons here. She sends up the weather balloon and says, okay, at 2 kilometers, I've just got my weather balloon reading, and it looks like that. That's my environmental lapse rate. That's the actual change in temperature with height,
So it's really dependent on where you go.
relative to whether it's
Well,
saturated or
yeah,
not.
so
Yeah,
like
so you go to this position and you say, okay, if it was unsaturated, it would be stable because it would be cool. If it was saturated, right, it would be stable because it's still cooler. So the most stable position you can have in an atmosphere is this. It's an increase in temperature with height. And that's known as, anybody know what that is? When temperature increases with height? It's known as an inversion. The inverse of the norm. When temperature increases with height. I know the question's coming. Well, how do you get an inversion? We'll get there too. Right? But that often happens. Especially on winter evening. When you've got cold air, all that cold air sinks down, and you've got a big pool of cold air here and relatively warm air above. Okay? Does that answer that question, Ron?
Yeah, so like when, with the line you drew on the board.
Yeah.
both Saturated, unsaturated, or stable.
Doesn't matter. Gonna be
So
stable.
like in that situation, you can't have an unstable atmosphere.
No. No, not in an inversion. Good question. Even in an isothermal situation where the temperature is not changing, you might love it.
It's gonna be stupid, but could they ever flip, like, could the moist?
No.
No,
Nope. Cannot. Good question. It's not a stupid question. It's a good question. So your dry adiabatic is always going to be to the left of the saturated adiabatic. It's always going to be variable and curved. And you got to look at where does the environment come in to play. Okay. So let's put this together. No potty break today. I'm afraid. Put this together in an ascent of a parcel of air from the surface up. Bearing in mind, you can actually go to any elevation in the atmosphere, but we're going to start at the surface here. So we've got altitude in kilometers and temperatures, no numbers, and here's your pulse, right? So Sloan sends back this line. That's the environmental lapse rate. Oh, there's an inversion, okay, and then it changes around and it decreases with height. That's the actual environmental lapse rate. Is this one? Oh, we should have done this in a different color. But let's do this as the environmental lapse rate. So that's the actual temperature and height. And then I say to you, determine the stability of that atmosphere. What is the likelihood of a parcel of air at the surface? If you could get it going, what's it going to do? Well, immediately it's going to cool at the dry adiabatic lapse rate, which is this curve here, the DALR, right? That's the linear curve. So it starts rising, and it's cooling, and it's rising and it's cooling. Is the atmosphere stable or unstable down here at the moment?
It's
Why?
on the right.
It's on the right, but I want a better explanation.
It's less than the actual temperature.
The temperature in the parcel is higher than the environment. The environmental lapse rate is less than the temperature, so it's unstable, it's unstable, it's unstable. And if it never reached saturation, let's say this was a super dry air mass, 20% relative humidity, okay? If this parcel of air rose, unstable, 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 and it rose along the dry, it would stop right there. And it would become neutral. It could not puncture through the environmental lapse rate, because here the temperature in your parcel is exactly the same as the temperature in the environment, and it would go, whoa, wait a minute. So you would see no clouds at all under that scenario. No matter how you tried to lift that parcel of air, if it kept going, and if it was unsaturated and never reached its viewpoint, right?
So the goal is entirely is just for the air mass to get to the same, I guess, the temperature as the surrounding environment.
Well, if you phrase it like that, that the goal is, if you don't want rainfall and you want to go and play golf and you don't want to have to start putting up an umbrella, sure.
So when you get rainfall and all that, clouds would be unstable.
Gotta be by definition.
You can't have a stable be like today.
I'll show you exactly what's going on.
So like with last night, because it was just like randomly, it just started to get really windy and it actually rained, like really.
Okay, so that wasn't, so here's
Does that
the,
matter?
yeah, it does. Here's the complicated factor, right? You can have a stable atmosphere, but when you put it up front, the front goes, the front is the royal flush. The front goes, I don't care whether you're stable or unstable, you're going up, right?
no.
Okay, so this is stable as so long as it remains dry, right? However, it's cooling at 1 degree Celsius per kilometer, and let's say it reaches its, what do we call that temperature to which it must be? It reaches its dew point, temperature to which it must be cooled for saturation to occur. Let's say it saturates here, right at this elevation. At 2.1 kilometers, that air now becomes saturated. It's now slid left right onto the saturation vapor pressure curve. Okay, now what happens? Now it starts cooling at the saturated adiabatic lapse rate. And if it reaches its lifting condensation level, which is the level at which the dew point occurs, okay, if it gets there, Still don't have a trigger yet, but if it gets there and you take your hands off it, now is it stable or unstable? It remains unstable because the temperature now will always lie to the right. Physically, it will always be warmer than the environment. So coming back to Ryan's phrasing, the goal here, if you like rainfall, the goal is to get to your lifting condensation level before it reaches the temperature of the ambient air.
So as it goes towards its equilibrium level, will then like clouds just disappear because it's at the same temperature as its surrounding environment?
No. So it's not that the clouds will disappear. You won't see any cloud unless there's something very local going on in terms of you may get a little puff of cloud if there's something wacky going on, but it's not that cloud. You won't get any clouds here. You've got to get to the lifting condensation to form clouds. And if you can get there before it reaches the environmental lapse rate, you're golden. Okay, it would then be unstable all the way through to the equilibrium level at the top.
So the SA and the DAR, they'll always blend.
So the not quite. So if I was to draw the dry adiabatic lapse rate, so let me see if I understand the way you're phrasing it. Here's the parcel, and let's say we're at the surface. We draw the dry adiabatic lapse rate, and you draw the saturated adiabatic lapse rate there. If you're just looking at that parcel at the surface, right? Then you would say, okay, it's going to cool at the dry, or it could cool at the saturated. Heck, it doesn't matter, because I've got such a steep environmental lapse rate. I'm always going to be that we're getting. Yeah. Yeah. Okay, awesome.
What happens at the equilibrium level?
It stops. The parcel stops rising.
Then does it sink?
It depends. It depends. It's conditional. When it gets to the equal, so this is actually known, we'll come back and do this in your take-home exercise, right? That's known as the limit of convection, the LOC, right? That's the limit to which any uplift will continue to occur. Keep firing, right?
So, in this example.
Yeah.
I see like the LCL is the solid on the dash, dry and moist on the dash. I just want to make
So
sure.
that's the dry adiabatic lapse rate. That's the saturated adiabatic
Okay.
lapse rate. The LCL occurs at that point.
Okay.
Yeah.
Okay. So what's the environmental one, the solid one?
Environmental lapse rate is a solid one.
Okay, and then what were you saying with if it gets to the LCL before this and you're before?
If it gets to the LCL here, meaning it's saturated, it'll continue to rise because it's still unstable.
So if the
Because now
LCL
it's
occurs to
cooling.
the right of that line.
Yeah,
Then it means you're probably.
it's just gonna keep going. It's just gonna keep going. Yeah. I love it. Let's go live. Let's go. No, let me explain what you're looking at and then let's go live. Okay, so this is a thermodiagram. This is what you're gonna take home and snuggle up to over spring break, focusing on nothing else to get 100 out of 100 for this exercise. So this is known as a sounding. This is the vertical sounding. That's all a thermodiagram. There are all sorts of different ways of plotting it. There's QTs and all things. We're just going to keep it nice and super simple. Let me show you what you're looking at here. Okay, it looks really bamboozling at first because you're going to have multiple lines, and the one I'm giving you is going to have even more. Oh joy! So what are we looking at here? So with a thermodiagram with a vertical sounding, well, this looks familiar. These are the mandatory pressure levels. In blue, 1,000 millibars, 987, right? So that's mandatory pressure levels. Okay. And the black lines here, this line here, hope you can see that. Okay. That line there is the environmental lapse rate. That's Sloan's data that she sends back. The environmental lapse rate. Is that visible from the back here? That the black line is there? Yeah. Okay, cool. Right? But there's a second line here. The second line here is the dew point. Awesome. So at each elevation, Sloan's now giving us a second data set, the temperature and the dew point temperature. How that dew point changes as you go up with elevation. Hang on to that for a second. What are the other lines you see on here? Okay. So the other lines you see on here are the green lines. So this is temperature down here in degrees Celsius. Okay, we're going to keep it degrees Celsius. The green lines are the dry adiabats. Dry adiabatic lapse rate. Linear, 1 degree per 100 meters, right? So all the green lines are the dry adiabats. Okay. The dashed blue lines, and you can see that they look kind of linear here, and then they start getting this funky curve to them. Those are the saturated adiabatic lapse rates, right? So you get all this on the diagram for you. You've got the dry adiabatic lapse rates, the saturated adiabatic lapse rates, the actual environmental lapse rate, and the dew point temperature, right? Awesome. The black here, these are the heights at which these pressure surfaces occur. So now we're coming back to that constant pressure surface at a certain elevation. So look at the 500 millibar height. The 500 millibar height occurs at 5,810. Okay. 5,810. Does that ring a bell? Would you say that's a high height or a low height? Think of it, green slopey line. 5,810. What did I say that average difference between the warm tropics and the cold poles would be? 5,900 to about 5,200-ish, something like that, maybe 5,000, right? So this is quite a high height for the 500 millibar surface. The jet stream is at 9.5 kilometers, right? Of course, we've got something else. Got to have this. You'll see how this becomes important. The brown lines. What are the brown lines? The brown lines refer to this scale down here. And the brown lines are the specific humidities. Okay, the specific humidities. Look at the units there. How many grams per kilogram? We're not going to deal with that for the rest of the morning, because that you're going to deal with in your take-home exercise. But those are the specific humidities. How many grams of water per kilogram of dry air, right? We also call that the mixing ratio. And then we've got what the wind direction and speed is doing with elevation. There's a boatload of information on a thermodiagram. But the data you need is so simple. We need the temperature, we need the dew point. Yeah, we've plotted the wind speed, and it tells you what heights the pressure is occurring. Okay? All right, let's go live. Let's see if this works. Hopefully, let's see. Here it is. Oh, beautiful. Let me see if it's been updated. I don't think it's been updated. And no, I don't want that the server's busy. That's not going to work for me. Shoot, it was just there. There we go. There we go. There we go. Okay. All right. So this is from the University of Wyoming. Okay. I'm so used to their graphics and I like them. So this shows, this is the station number, Fort Worth, 00Z 27th of February. What's today? 27th of February. So this is still dated. They haven't updated the morning one. This is 6 p.m. last night. Okay. So 6 p.m. last night, minus 6 hours from that. Right. We've got the temperature in degrees Celsius. Okay. We've got the green dry adiabatic lapse rates. We've got the blue curved saturated adiabatic lapse rates. Wyoming uses the purpley ones for the mixing ratio. We've got wind directions and pressures and so on. Solid lines are temperature and dew point. And then here, and I'm going to do this in blue, yeah, I'm going to do it in red. You can maybe make it out. Here is from the surface there, is the temperature there, and what the parcel would do along the saturated adiabatic pressure. Yeah, that's pretty good. So this is taking the surface parcel, forcing it to rise until it reaches its dew point, and then forcing it to rise at the saturated rate. 6 p.m. last night. So what are we doing?
Is that line following a curve that's already there?
Nice observation. That was going to be one of the things. Hold on to that for a second. Just look at the environmental lapse rate, which is the black one just behind there. And it does that and it does that relative to the dew point. Someone talk to me about the relationship between the environmental lapse rate and the dew point above Fort Worth at 6 p.m. last night. How would you describe the air about 6 p.m. last night?
Unstable.
Okay. Why? You see your reasoning there? So, okay, I'm glad you, okay. This is the dew point. This is the actual environmental lapse rate. So let me rephrase that. How would you describe the air above Fort Worth in terms of the humidity? Hmm?
Yeah, really, because it's closer to the.
So there's the air, and here's the dew point. This dew point is, so this is interesting. They actually, no, they don't have the surface here. The dew point, the surface dew point is actually somewhere down here. So it was reasonably humid-ish. Okay. The temperature here, that's 25. That's what's the temperature last night? 78 degrees Fahrenheit, something like that. It's pretty nice. I almost put on the barbecue last night. Okay. Because these temperature lines are going vertically. Now look at the relationship between the temperature and the dew point vertically. Well, let me come back to your question. How would you describe the atmosphere last night in terms of stability? Looking at your theoretical parcel rise, red, versus the actual temperature, environmental sound moving slow. Right.
Some codes.
Temperature is decreasing with height. It's getting to its dew point, and you can see it changes here to the curved line, meaning by definition, this last night was the, what do we call this when the air temperature reaches its dew point? And we call it the lifting LCL, okay? Come back to the first part though, talk about stability. Is the lower atmosphere stable, unstable, or neutral last night?
Neutral,
Why?
because it's on the follow.
Bingo, right? I said neutrality is actually more of a rarity. It wasn't last night. Conceptually last night, the environmental lapse rate was pretty much right on top of what the dry adiabatic lapse rate was as you started going from the surface up. Okay, did we have any storms or uplift last night? No, not really. Okay, it's complicated because we had this frontal boundary. What else do you notice about that actual environmental sounding? You're going to have to do this in your take-home exercise, and you're going to get questions on the integrated assessment like this.
If it's on the saturation curve, why does it like skew right a little bit? And then
Where?
like, go up? Right there, why does it skew right?
That?
Yeah.
What is that? That's the actual environmental lapse rate. Why does it skew right? What do we call it? Because it increases with height. Hello, there is an inversion. Temperature increases with height. Just for a little bit. It's only, look at the heights here. We're talking about a couple hundred meters. Is that air moist, dry, or super dry in that inversion? Why? How can you tell whether the air is dry in that inversion? The what? Dramatically. Dew point is meandering up here and then it goes. Dew point tanks. It just collapses, right? The dew point goes left. And as the temperature and the dew point diverge, the air is really dry. Make sense?
But does that mean it's no longer saturated?
Absolutely.
Then why is it following that red line?
Because it's a conceptual red line.
Oh,
Right, I know it.
that.
This just
Okay.
sucks. A lot of this is hypothetical. Audrey's not enjoying hypothetical games. Like, what's going on here, right? The black line is the actual increase in temperature with height. The black line to the left is the dew point, the actual dew point, right? This red line is, okay, what would an air parcel do from the surface vertically? How would we describe stability of our parcel from the surface? What is the likelihood that a parcel at the surface, if we can still get this darn tree, what is the likelihood of that air parcel rising up through the atmosphere?
Why do you say it gets saturated when the two curves don't actually ever touch?
These two,
Like there don't,
the red line is the conceptual dry adiabatic cooling, and it's the conceptual lifting condensation level. So to your point, these two lines must touch. If they touch, that means it's reached the lifting condensation level. It's actually reached the dew point. Okay, let me back out here for a second and redo this. A great question, right? We take that off here. What I'm saying is the black line on the right is the actual environmental lapse rate. That's exactly what temperature is doing. This is the dew point temperature, right? The dew point never touches the actual temperature. In other words, the lower atmosphere last night never reached its dew point. It never got onto the saturated curve. So then you're probably thinking, well, why are you drawing the saturated curve here? This curve is the what if curve. What if we take a parcel of air at the surface last night and we lift it at the dry adiabatic lapse rate? And what if at that cooling rate, it reaches its theoretical dew point at that cooling rate? The truth is nothing, right? Because one is it's basically neutral, and then you've got this inversion. And any air parcel, even if it reached its lifting condensation level, it would stop right here at the inversion. Inversions are the most stable state of the atmosphere. An inversion literally acts like a lid. You may as well just take the lid on your saucepan and go and put it on the atmosphere. Right? So we've got a dry influx of air here coming in that inversion. Does that make sense?
Why do we say that it reaches lifting condensation level then if it didn't reach the dew point?
So this is so what you're doing here is you're taking, it's a good question. You're taking the air temperature of your parcel here, and you're taking the actual moisture content of your parcel here, right? And you're saying if that parcel was lifted at that moisture content, it's a really leading but key question, and I didn't want to go there because it's potentially confusing, but I'll answer it. If you take that parcel of air at this temperature and at that dew point there, right, and you say, I'm going to take my little darn pesky bubble, and if I could lift it, it would cool at that dry adiabatic lapse rate. And based on the moisture in that air bubble, it should reach the lifting condensation level here. The challenge is dew point changes. Shoot, that's the challenge. Okay, we'll come back to that later on. Okay, so we're just dealing with, is that lower atmosphere stable or not? And it turns out, up to this point, it might if you've got a trigger, but nothing more than that, unless you can get rid of that inversion, right? Okay, so that's what's going on above Fort Worth last night. What you want, if you want catastrophe, here's what you want. You want to heat the ground, you want to get to a dry there, you want to reach the dew point there, and you want to do that. You want everything to lie as far away to the right of your environmental lapse rate as you can. Okay, but that's not what's happening outside last night. Okay, so let me just pop back to the PowerPoint here in a second. Okay, for some reason, okay, I'm going to have to. I think, let me just see if that's a, yeah, so here's a good summary table at the end. So this is the ramifications of stable air versus unstable air, right? And you probably think, gee, it's done an hour and 20 minutes, but it's just so critical because I know there's a lot of conceptualization here, and then we're going to put it into practice on an actual thermodiagram. So stable air, right? Stable air is generally sinking, suppression of rising motions, lack of surface, bless you, warming, right? Air stability in a high pressure where your air is slowly sinking, that's generally stable air. Low pressure where your air is rising quickly, that's unstable air, right? So it's defined by a rapid change in temperature with height. Okay, we'll get to this caused by surface warming next week. I know we haven't even touched the triggers yet, right? This is all just looking at, here's the environment. What's that fossil doing relative to the environment? Okay. Take that number. All right. We're done. That's good. We'll come back and talk triggers, clouds, and precipitation on Tuesday.